Hi, Professor Bob Young back at you here, and in this instructional video we're going to talk about exponents and properties of exponents, exponential functions, and solving a few exponential equations. So I want to refer you to the supplemental handouts in Angel, or what was given out at the beginning of course if you were a lecture or hybrid student, the handout on 5 essential power rules. So we'll just kind of run through those very quickly here and refresh your memories, and this should be review for most of you. So power rule 1 says, whenever you multiply same bases, add the powers. So remember, a number in exponential form, a in this top part is the base number, and 7 is called the exponent or power. And it's very advantageous to write a to the 7th power, because really what does that mean expanded? It means, well, a times a times a times a times a. How many times? Yes, 7. And I want even more than this on the next test. All right, so rule 1 says when multiplying same bases, and we'll just take some real basic examples here. If you expanded all of those out, you would get x to the 7th power. Similarly, if you divide same bases, and we can pick any letters here. I mean, we could pick c to the 5th over c squared and just subtract the powers there. So again, if we expanded those, it would be 5c's divided by 2c's, and if you canceled out 2c's, anything divided by itself is 1, and you would be left with 3c's. Power rule 3, anything to the 0 power is 1. Now, if you don't believe me, try this on your calculator here. Now, to do exponents on your calculator, most of them have this caret key here to raise something to a power, so you could go 5 caret 0, and your calculator will give you 1. Why, Young, why? Well, to get a 0 power, you would really, using that second rule we just learned, if you subtracted the exponents, you would get 5 squared divided by 5 squared would give you that 5 to the 0 power. Now, really, when you get something to the 0 power, let's look at this. You're really dividing, if we took 5 squared, the same number by itself, and that's why you would get 1 there. Okay. Rule 4, the negative power rule. Now, what if we had, let's say, and I'll pick some other letters here, f, which we don't want on the next test, squared, divided by f to the 5th power. Well, if we subtracted the powers there, we would get f to the negative 3rd. Now, they call this f a misplaced base. And if you think about this, if we expanded this one over here on the side, we would have 2 f's in the numerator, 5 in the denominator. So if you think about this, whenever you cancel or divide the same thing by itself, you get 1, and we would have 1 over the f's would be where? In the denominator. So they would rather write this answer 1 over f to the positive 3rd power versus that negative power there. So that's where that rule comes from. So just remember this, if you have a negative power in the numerator, you can make it positive by bringing it to the denominator and vice versa. And you'll see lots more examples here on the handout. And the 5th and final power rule states, whenever raising a power to another power, multiply the powers. It's like playing poker here. So on this one, if you have x to the 8th power raised to the 10th power, and I kind of remember that because of the old, parentheses usually mean multiply. Multiply to get x to the 80th. So there's a quick review on your basic exponential rules. Now, next what I want to talk about, I'm going to plant some seeds in your mind now for the rest of this chapter we're going to be heading into. All right? And I like that old show ER. I don't know if y'all remember that show. Some of you younger students may not, but it was on many years. And anyway, had some good drama. I like to take, whenever you have a fractional exponent to some base, so I called here some base number b, and I called this b raised to the e over r power. Now, what I'm going to call e over r here, when I'm talking exponents, is I'm going to say e is the exponent divided by r is the root number. So Young likes to use that show ER to show that. So notice that any base raised to a fractional exponent is a radical in disguise. So b to the e over r power will be the rth root of b raised to the e exponent there. And notice that exponent, you can leave it inside with the b under the radical, or you can bring it outside to get the same thing. So let's take some numbers here. I know all these variables, sometimes students will go, what? 16 to the 3/4 power. Now we could write that as the 4th root of 16 cubed. Now, I don't know what 16 cubed is without my calculator here. I might have to actually get my calculator for this lesson. But it would be if I took that 3 and moved it out, I do know what the 4th root of 16 is without a calculator. That's 2. So notice this would be a nicer way to do it, and you would get 2 to the 3rd power is 8. A few more examples. Here's, a fractional power that's negative, Young. But remember, we talked about that 4th rule. You can take that negative power in the numerator and bring it down. It becomes positive. Notice we can then take the e over r here. Now, I better get a pretty blue out. Young, where's the r number? Well, they didn't put 1 there because anything to the 1st power is itself. So they got 1 over the cube root of 27 to the 1st power is 1/3. All right, they did the same thing with this next example. 64 to the negative 1/2 power, they brought that down. And notice the 1/2 power on a square root. Did y'all notice they never put the 2 in there on a square root? Why is that? I do not know why they don't put the 2 in there, but it's really there. It's the square root of 64 to the 1st, which we know the square root of 64 is 8 here, so we get 1/8. Now let's do it with some variables. If we have x to the 2/3 power, remember the old e over r rule, this would be the cube root of x squared, okay? Or the 4th root of y, or y to the 1/4 power, I'm sorry, I got ahead of myself there, will be the 4th root of y, or y to the 1st. So just a few little exponential things. We're going to need these as we continue throughout here. All right, now evaluating some functions here. So we're going to go ahead and let f of x be 2 raised to the x power. That's why they call them exponential functions. And g of x be 1/3 raised to the x power. So we're going to go ahead and evaluate this, some of these here. So f of 3, plugging in 3 wherever we see an x up top here, would give us 2 to the 3rd power, which would be 8. F to the negative 2 power would equal 2 to the negative 2 power. Oh, there's that negative exponent. I know that bothers some of you. Don't panic. We're going to take it and move it down here. So it would be 1 over 2 to the positive 2nd power using that 4th power rule. And if you want to stop the video and back it up, you can look at that. It would give us 1/4, the fraction. F to the 1/4 power would equal 2 raised to the 1/4 power. Now, I might need my calculator for that one because I don't know. I mean, or we could write it as, you know what, the 4th root of 2 if we wanted to. And then we could evaluate that on our calculator, and they may have you do that and write some decimal values there. Let's get to the g function. G of 4, I know you love these fractions here, would be 1/3 to the 4th power, which, remember, that would be 1/3 times 1/3 times 1/3 times 1/3. So 1 times 1 times 1 times 1 in the top would be 1. 3 times 3 times 3 times 3 would be 81 in the bottom. These are fun, huh? All right. G to the negative 2 would be 1/3 raised to the negative 2 power. There's that negative exponent here. Now, if we were to take that here using the 4th power rule, or I'm sorry, the 5th power rule, we could put little powers inside here on the 1/3. We could say that's 1 to the 1st over 3 to the 1st. We could multiply the powers, so I could go a lot of different ways with these things. So I would get 1 to the negative 2 over 3 to the negative 2 power. And then if I want to rewrite those using positive exponents, I would just take one to the top, the other to the bottom, and I would get 9 over 1, or 9. Now this last one we're definitely going to need a calculator for. So we've got 1/3 raised to the, oh my gracious, 1/3 raised to the 2.45 power here. So I do not have my calculator out. I'm going to have to get it out here. Young, why aren't you more prepared? I forgot I put one of these sneaky ones on here. I want y'all to try this and be careful. When you put the fraction 1/3 in, you may want to use parentheses on it like that. And then hit your caret key and 2.45. So you and your calculator, this chapter will have to become 1. And I am getting my calculator out right now, and I'm doing this. So I'm putting parentheses, 1 divided by 3, caret 2.45, and I get about this decimal answer here. This is approximately 0.06777 2409, and this is going to be one of those numbers that goes on without end. It doesn't end and doesn't repeat. So they may want you to round it like 3 or 4 places. Rounded 3 places, let's say it's about 0.068. What do y'all think? So that would be the number that would make 7 round up to 8. All right, so just some evaluating some exponential functions there. Now, this is going to be important as we get to you-know-what. Yes, graphing. Some of you going, no, not graphing. They say no. So notice there's some really cool things that we can look at when we graph exponential functions. Now, I'm going to look at the graph on the left first here. And actually, I should probably put some pretty lines here on this. This is the graph of y equals 3 raised to the x power over here. So I'm going to go ahead and sneak that in here, y raised 3 to the x power. And if you think about it, let's make a little list of points here. We can do that on this one. We can put 0 in for x, which would give us 3 to the 0 power. Y would be 1. And I'll come over here and I'll show you right there. Whoop, there it is. There's a point on the graph. When x is 1, you get 3 to the first power is 3. And I'll kind of come up here. Whoop, there it is. I'm trying to hit it with my writing tablet. It's kind of slidey and hard sometimes. 2, 3 squared is 9. It's about up here on my writing tablet. I'm not doing too bad. I can make that other point a little better here. Okay, you can see that graph happening. Now watch what happens when x is negative 1. You get 3 to the negative first power, which we learned that, hey, you got to bring that down 1/3. So negative 1, this thing starts coming down here a little under 1, 1/3. Negative 2 is 3 to the negative second power, 1/9, and so forth. Now, think about this thing if we went way out there, like to the negative 100th power. Oh, my gracious, young. We would have 1/3 to the 100th power, which would be some really big, small decimal. We would be getting closer and closer to 0 without ever touching it. So this graph will never touch the x-axis. Y will be smaller and smaller and get closer to 0 without ever getting to 0. What a concept, huh? So guess what's back here? The horizontal asymptote. So notice here as x, and I'll write this like you might see later on in more advanced courses, as x approaches negative infinity, y, or f of x, approaches 0. And that really is the true heart and meaning of what an asymptote is. All right? It approaches there, but never gets there. So notice some important features of exponential functions here. And what happens on the other graph here is when this a number is between 0 and 1. So let's say we have the function here, y equals 1/2 raised to the x power. So this a shouldn't be in here. I don't know what happened there. That should be 1/2 raised to the x power here. So something happened in that graphic, but we'll fix it. All right, so when that a number is a fraction, notice that this graph just kind of goes the other way. And if we were to get some points real fast here, and we're going to graph some more of these, we could put 0 in. 1/2 to the 0 is 1. Here we go. 1/2 raised to the first power is 1/2. See, so this one starts getting smaller over as we go larger on x. 2 would be 1/2 squared, which would be 1/2 times 1/2, 1/4, and it's getting closer and closer again to x. But it will never, what? Cross or touch it. And then if we went -1, watch what happens. We get 1/2 to the negative first power. We use our reciprocal rule there, which gives us the number 2. So as x goes negative, look what happens here. This starts getting larger this way. So they kind of have a similar look. So this base number a, when a is greater than 1, the graph will look like this. And when it's a fractional value, it'll tend to look like that. All right, so here's some important features of exponential functions, and you can see it on both. The domain, all real numbers. Look at those x values. They'll go left, they'll go right. The y values, the range, 0 to infinity. Notice the parentheses on the 0 here. Does not ever get to 0. When a is greater than 1, the graph looks like the left graph. When it's between 0 and 1, it looks like the y graph. And this fifth rule, when we solve exponential equations, we're going to come back to. A to the x equals a to the y, if and only if x equals y. That's how we'll finish up this video. All right, let's graph one more of these real quick here, and this is what they'll ask you to do. Graph the exponential function y equals 4 raised to the x power. Now, if you think about it, going back here, will this one look like the left graph or the right graph? Did you notice things disappear magically when I went back? Oh, Young, how do you do it here? It will look like the left graph, I think. So putting in some points here, when x is 0, we get 4 to the 0 power, y is 1. 1, 4, 2. Now notice when x is 2 here, man, that thing shoots off the graph, 16. -1, 1/4. -2, 1/16. And we'll see what happens here. So let's start plotting the points. I tried to make a little better graph paper this time, like the graph paper I like to give y'all on tests. Now notice 216, it's 216's on up there. I can't even get to it. But -1, 1/4, -2. So this thing's going to start getting closer and closer and closer to x without actually getting there. And man, this is really a challenge on my writing tablet, but that's about as good as I can do. So here we go. Domain, -infinity to infinity. Range, 0 to infinity, the y values. And the ha on this one, y equals 0. Okay, so remember the ha in this case is the x-axis, and it crosses y here. That graph will never touch or get below this right here in pretty blue. Okay. And here is a similar graph, and I just plotted some points for 1/2 raised to the x power. This is one we've already talked about here. And again, it says the x-axis is a horizontal asymptote as x approaches positive infinity here. Now, let's get to some shifting. Woohoo! Because they're functions, and we learned this in previous lessons, passes the vertical line test. Notice the graph here. I've got a vertical shifting of f of x equals 3 to the x power. So in red here, I'm going to put this, and y'all know I like to play with the colors here. This would be y, or f of x, equals 3 to the x power. Notice what happens in blue. If I move this thing, I put a +2 on it, it does the old vertical shifting 2 units up. And not just does the whole graph shift 2 up, but guess what else here that I'm going to now sneak in here shifts 2 up? The ha on a vertical shift on this blue graph will be the line y equals 2. What do y'all think? And then Young's going to go to black here. And notice if you go y equals 3 raised to the x power -4, anytime you add or subtract a number to any function, that's your vertical shifting. That one's going to go 4 down. And the ha, if I were to draw it again, will go 4 down. y would equal -4 for the ha. And of course, you could get points and graph those as well. All right. Also, Young, you're doing it again. What are you doing again here? Oh, the shifting is back. Just a little good exam review from previous sections. Y equals 3 to the x. There's my base one here. Now, in blue, look what happens if I take and I put y equals 3 to the x raised to the x minus 2 power. It's the old horizontal shift, the direction you don't expect, 2 units that way. And going back to black here, y equals 3 to the x plus 4 power shifts 4 units horizontally that way. Now notice here, has the ha changed at all on any of these graphs? Our friend the ha on all of these, if it shifts left to right, does not change. It would still be y equals 0, so the shifting is definitely on. And even when you put a negative in front of a function, remember that. It's the old flips about the x-axis here. So when you take y equals the 3 to the x and you put a negative, oh, I'm sorry, not a negative there. Rats, negative here, I'll get it. It will flip that graph about x. So all of the shifting things we've talked about in previous lessons apply to these exponential graphs. So notice here, I gave you a whole bunch of them here in all different colors here. And notice what happens when the exponent gets larger, like if we go from 2 to the x to 3 to the x to 10 to the x, and then the other way around with fractions. I mean, if you ever get an exponential chance to increase, let's say you've got an investment that grows exponentially, take it, because it will constantly increase if that base number is what? Greater than 1. Now, don't take the investment if the base number is a fraction, because then you'll lose money. It'll constantly decrease. All right, last thing we're going to talk about, as promised, that little exponential rule, solving exponential equations, and we looked at this earlier. Remember that if a to the x power equals a to the y power, if and only if x equals y. So here's a method to solve exponential equations. And what this says is, I'm going to try to get all these base numbers the same. So in order to solve this first one, I'm going to call 4 2 squared raised to the x power. And I'm going to leave 2 alone. I'm just going to say 2 is 2 to the first power. So if you're going to solve exponential equations, one method here, and this is what this is saying here, if you can get those base numbers the same, well, then their exponents here, I'll put those in red. I know the color's still here. Will always be the same. Now, Young, what do I do here? Whenever you have a power raised to a power, oh, you've got to know those power rules, ladies and gentlemen. Yes, multiply the powers, and you'll get 2 raised to the 2x power equals 2 to the first power. So we have accomplished what this rule up top says. So once we get those bases the same, we can go ahead and set the powers equal to each other. So look how nice this will come out. 2x equals 1, x equals solving 1/2. And if you can check that on the test, you can put 4 raised to the 1/2 power on your calculator, and you'll get 2. Or you could remember that 4 to the 1/2 power really means in E over R, the square root of 4 to the first, which is 2 as well. So there's the first example. Example 2, you know Young likes to give you lots of examples here. Guess what common base we're going to use on the second example? Well, we've got 5 here to the 2x minus 1 power. I think I can get 125 in terms of base 5, and it would be 5 cubed. So again, once you see that, you will just take those powers, set them equal here. You can circle the wagons. You can go to colors here. So once those bases are the same, the powers, set them equal, and you can solve here. Add 1, 2x equals 4. X will come out to equal 2, dividing by 2. And again, if I put 2 in here for x, 2 times 2 is 4 minus 1. I will get 5 to the third power, and that will certainly give us 125. All right, the next one. Now, this one's really going to blow your minds here. I think we're going to have to get 27 and 9 in base 3 form here. So this is one of the tougher ones you'll see, these last two. So we'll have to say 27, you'll have to see this, is 3 cubed raised to the 2x power. 9 will be 3 squared raised to the x plus 1 power. So once you get those bases the same here, now what do we do with these powers? Again, powers raised to powers. This will become 3, multiply them to the 6x. You got to know those rules from earlier on. 3, 2 times x minus 1, or I'm sorry, x plus 1 will be 2x plus 2 power. Gracious, John. And then just take those powers and set them equal. So remember, we had to do power rule number 5 here and here once we got those bases in terms of 3, multiplying the powers, and then we can easily solve these linear equations. 4x equals 2. This one, x would be 1/2. All right. Now, the last example, I may let you finish here, or maybe I'll go ahead and do it here. We're going to get base 3 again. Now, notice when we've got 1/3 to a negative exponent, if we were to take and flip it, do the reciprocal rule, we would get 3 over 1 to the positive 4x equals 81 is 3 to the 4th power. And of course, 3 over 1 here reduces to 3. So this last one, you just get 4x equals 4. Watch those negative powers, do that reciprocal rule. So you have to know your exponential rules in this chapter, and you'll get x is 1. All right, Bob Young signing off. We'll see you in the next instructional video.